Okay. Now, we slipped one thing by you. We said in South Africa, the risk for heart disease is about 5% in this age category. But in our sample, we've got 160 cases and 302 controls. So in the sample, we show in a risk of 0.35. So it seems like the model's going to be off. It's going to estimate probabilities too high. Well, case control sampling is one of the favorite tools in epidemiology, especially when you have a rare disease. You take all the cases you can find, and then you can just sample from the controls. And the reason is that for the logistic regression model, it turns out that you can estimate the regression parameters of interest, these are the coefficients of the x's in this case, accurately. That's if the model's correct. But the constant term will be incorrect. And then you can just go ahead and correct the constant term by a simple transformation. And in fact, for those that are interested, I just give you the transformation. So pi tilde here is the apparent risk of heart disease, in this case, in our population, which is 0.35. And this is, after all, this is just the logit transformation of the prior probability, or the prior apparent probability. And here's the logit transformation of the true risk, which is pi, in this case 0.05. And so we take the logit transformation of those two, and we correct the intercept. This is the currently estimated intercept, and we correct it by adding in the log odds of the true probability, subtract the apparent one. That corrects the intercept.
Maybe it's worth saying a little about case control sampling, right? Like why the sampling was done this way, right? One thing we could have done instead, or the investigators could have done, was to take maybe 1,000 people and to follow them for 20 years, right? And to record their risk factors and then see who gets heart disease. And we think about 5% would get heart disease. And that's a valid thing to do, but the problem is it takes 20 years and maybe more than a few thousand people to get enough. Actually, with 1,000 people, we'd get, 50 cases, right?
Right.
But, so that's not very practical. We need a large sample, and we need many years to do it.
Right.
Case control sampling says, well, let's not do things prospectively like that. Let's rather find people who we already know have heart disease or don't have heart disease, and then sample them. And now in the proportion, in this case, we'll take 160 cases and 302 controls, and then record their risk factors. So we start with cases and controls, and we get lots of cases, and we can do this without waiting 20 years. We can do it right now, and then we record the risk factors.
Yeah, that's a good point, Rob. Yep. And that's a very popular in epidemiology. There are other issues involved with case control sampling, retrospective sampling, but we won't take that up now. But that's the reason it's so popular. On the same issue, in many modern data sets, we have, we'll have very imbalanced situations. For example, if you're modeling the click-through rate on an ad on a web page, the probability of someone clicking is less than 1%, maybe 0.005 or even smaller, 0.001. Which means if you just take a random sample of subjects who've been exposed to ads, you're going to get very, very few ones and a huge amount of zeros, okay? And these data sets get really large. So the question is, do we need to use all of that 0-1 data to fit the models? Well, from what we've told you, no, you can take a sample of the controls. And this picture over here just gives an indication of the trade-off. The point is, the main point is that ultimately the variance of your parameter estimates has to do with the number of cases that you got, which is the smaller class. And so what this plot shows is it's showing the variance of the coefficients as a function of the case control ratio, or in fact the control case ratio. And what it says is when you've got about 5 or 6 to 1, the variance kind of levels off here, and so there's diminishing returns in getting even more controls. So if you've got a very sparse situation, sample about 5 or 6 controls for every case, and now you can work with a much more manageable data set. So it's very handy, especially in modern, extremely large data sets.
So just a comment about what this case control sampling is. The most obvious way to study the risk factors for heart disease would be to take a large group of people, maybe 1,000 or 100,000 people, follow them for maybe 20 years, record their risk factors, and then see who gets heart disease and who doesn't after 20 years.
If you're still around.
If you're still around, if we're still around, right. Now, that actually is a good way to do things, except it's very expensive and takes a long time. You got to get a lot of people, and you have to wait for many years. Case control sampling is more attractive because what you do is rather than taking people and following them forward in time, you sample people who you know have heart disease. You also get a comparison sample of people who do not have heart disease, the controls, and then you record their risk factors. So it's much cheaper and it's much quicker to do. And that's why case control sampling is a very commonly used technique in epidemiology.
Okay, what if we have more than 2 classes? Can we still do logistic regression? Well, we can. It easily generalizes to more than 2 classes. So and there's various ways of doing this. And one version, which actually is how we do it in the GlimNet package in R, which you'll be learning more about, is we have this exponential form that we saw before, but modified for multiple classes. So notice in the numerator, we've got a e to the linear model. And this is for the probability that y is k, given x, small k. And we've got, say, capital K classes, where capital K is bigger than 2. And in the denominator, we've just got the sum of those exponentials for all the classes. So in this case, each class gets a linear model, its own linear model, and then we just weigh them against each other with this exponential function, sometimes called the softmax function. Okay. The Mathias students will recognize that some cancellation is possible in this ratio. And that's true. And what that means is actually you only need k minus 1 linear functions, as you do in a 2-class logistic regression. That's somewhat of a detail, and it turns out for our GlimNet application, this is a more symmetric representation, and it's actually more useful. This multi-class logistic regression is also referred to as multinomial regression.